let's talk about the concept of Lewis structures, okay? So whenever you have covalent bonds, the way the bonds are connected to each other is described by something called Lewis structures, okay? Let's take an example. Let's say we're looking at a molecule of water. Once we look at the molecule, well, we understand there's 2 hydrogens and 1 oxygen, but what we do not understand is how are the hydrogens connected to the oxygen, how are the hydrogens connected to each other. For example, are the hydrogens, is it possible that the hydrogens are connected to each other like this and then to the oxygen? Or maybe the hydrogens are connected to the oxygen and then the oxygen to the hydrogen, okay? And for each of the possibilities, we have to kind of use some rules of logic to kind of figure out what's the correct option. So let's take a look at some of the rules of how to write Lewis structures for elements. So the first, but before we kind of dive into actually writing the Lewis structures, we do need to remember the octet rule. But then there's another rule I'm going to explain to you out here. It's kind of like a rule that just is a helpful guide, okay? So the rule is this. It kind of helps us understand how many bonds. So it's called the honk rule. And the honk rule, basically, whereas is the H stands for hydrogen, O for oxygen, N for nitrogen, and C for carbon. And the H out here, if it's hydrogen, hydrogen forms 1 bond. Oxygen tends to form 2 bonds, nitrogen 3, and carbon 4. So really, this is the honk 1, 2, 3, 4 rule, okay? Now, this rule can be extended where instead of oxygen, sometimes you could have sulfur, okay? It would also form 2 bonds. Now, sulfur does have some exceptions, and we'll look at that later on. Instead of nitrogen, you could have phosphorus, and phosphorus has 3 bonds, same as nitrogen. And instead of instead of hydrogen, the H can also stand for, I'll write it out here, halogens. Halogens would be fluorine, chlorine, bromine, and iodine. Again, typically these will form 1 bond like hydrogen, but they can form more than 1 bond in certain cases, especially when you look at bromine and iodine, okay? All right, so right now we're just going to keep it real basic, and we're just going to look at hydrogen, oxygen, nitrogen, carbon, 1, 2, 3, 4. And then the other rule I want you to remember is the octet rule, where everything wants to get 8 valence electrons. Every atom wants 8 valence electrons. And then couple that with the duet rule. So this basically means when you have hydrogen, hydrogen wants 2 valence electrons. Okay, so in order to apply this, we're going to call valence electrons, we're going to just abbreviate them as VE, okay? So let's take a look at a simple example. Since we looked at water, let's go back and look at water and try to figure out what would the Lewis structure of water be. So the first thing you want to do is look at the periodic table and figure out how many valence electrons does each of the elements in water have. So there's 2 hydrogens. Each hydrogen actually has 1 valence electron. And since there are 2, that means we have 2 valence electrons for 2 hydrogens. The oxygen, it has 6, 1 oxygen, so 6 valence electrons. You add them up together, that gives you a total of 8 valence electrons, okay? Now that you have 8, now we have to use these rules, okay? So now if you look at the honk 1, 2, 3, 4 rule, that's the first rule we're going to look at to figure out how many bonds each one is going to have. Typically, the one that has more bonds is the atom that ends up being in the middle, and everything else ends up being terminal, meaning at the ends. So between oxygen and hydrogen, you can see that oxygen forms 2 bonds and hydrogen forms 1. So we're going to put oxygen in the middle. And then what you want to do is you want to basically use the rules of symmetry, which simply means that you're going to make the structure as symmetrical as possible. So you flank it with 1 hydrogen and you flank the oxygen with the other hydrogen on the left side. And see, now each hydrogen has one bond, see, one bond. And each oxygen, in this case is only one, has two bonds. Okay. Now, quick side note about bonds. Notice carefully how I drew a bond with a straight line. So, a bond, the way you depict bonds is a single line denotes one pair of electrons, and it's called a single bond. A double line is two pairs of electrons, note, and it's called a double bond. A triple line is three pairs of electrons, called a triple bond. Okay, how are these lines depicted? I'll write them in red out here. That's a single line. A double line is depicted this way, and a triple line is depicted this way. So basically they're horizontal lines, not vertical, not any angle, they're just horizontal lines. All right, so in this case we just have the case of single bonds. Now, coming back to Lewis structures, each bond is two electrons, right? See, a single line is equal to one pair of electrons, so that's two. And there's two single lines connected to oxygen. So how many of these valence electrons did we use up? 2 and 2, 4. So you subtract how many you used up to give you how many are remaining. So there's 4 valence electrons remaining. Those 4 valence electrons remaining will be put on the central atoms. You're going to first look at the outer atoms. Okay, so the rule is first look at the outer atoms. Are the outer atoms happy? Are they satisfied? Do they have a complete valence shell? Well, because they're hydrogens in this case, hydrogen needs 2 valence electrons, so it does have a complete valence shell. So we're going to go to oxygen. Is oxygen happy? Well, oxygen only has 4. Oxygen wants 8. So those remaining 4 will be paired up. So you're going to put 2 on top and 2 below. And there you have it. That is the Lewis structure of oxygen. Notice carefully how oxygen has 8. 2, 4, 6, 8 valence electrons, and each hydrogen has 2. And that is the complete Lewis structure of water, H2O. At this point in time, I'd like to also introduce the concept of shapes. We drew this in a symmetrical fashion, but then the question arises, what is the shape of this molecule? Okay, so when we talk about shapes, there is a theory called VSEPR theory that helps us predict the shapes. Okay, VSEPR stands for valence shell electron pair repulsion theory, VSEPR. Okay, so what this basically means is just fancy talk for saying that if you look at the central atom out here in this molecule, all these electrons are negatively charged species. So there are how many electron groups out here? There's one electron group, there's another one, and another one. So there are 4 electron groups, and these 4 electron groups are all negatively charged electron groups. They're going to try to push away from each other. Okay, so you're going to look at 4 electron groups, and you're going to try to figure out in 3 dimensions how will these electron groups stay furthest away from each other. Notice carefully, this molecule is drawn in 2 dimensions. In reality, this molecule exists in 3 dimensions, which means it's not going to look like this. In 2 dimensions, these seem like they are furthest away from each other. The reality is, in 3 dimensions, this is not how it would look. In 3 dimensions, it will look more like a tripod. And what we mean by a tripod is, I'll draw it out here. You would have the oxygen in the center, and then you'd have the 2 hydrogens coming out at angles to each other. This angle is actually 109.5 degrees, okay? And then you'd have the lone electrons, which would kind of look like this. I'll just draw them as lobes. That's how they're drawn in chemistry. And I draw the other one, which is actually going to be going behind the plane of this board, okay? So I'm going to draw them like a very light line. Okay, so that's going behind, okay? And what you're going to see is, and this one of the 2 hydrogens, one is in the plane of the board and one is actually coming out towards you. So I'm going to make this a little dark because it's closer to you. Okay, so that's kind of how it's going to look. It's going to be 3 dimensions. This shape is called a tetrahedral shape. So anytime you have 4 electron groups around a central atom, it's going to take the shape of a tetrahedron. Therefore, it's a tetrahedral shape, okay? Now, in order to predict the shape of the water molecule, once you arrange the 4 electron groups, then you just ignore the lone electrons. So you're going to put your hands over the lone electrons, put your palm, cover the lone, and I'm going to use this eraser and cover the other lone. And then look at what shape results. When I cover both the lone electrons, what you have is a bent shape. Okay, oftentimes it's also called a V shape. If you cannot take this and just switch it around, just spin it around, it looks like a V. But most often it's called a bent shape. Okay, so the water molecule, even though it looks linear out here, in reality it is bent. So the shape of this water molecule, I'll just write it out here, is bent. Okay. And this is kind of a good practice. So what you're going to do is, I would highly encourage you, when you draw the Lewis structure, also try to predict the shape that's going to result from the Lewis structure. Okay, so to summarize all of this, remember you start with the honk 1, 2, 3, 4 rule, then you count the valence electrons, then you use the rule as a guide to draw a structure, and then you go to the octet rule and the duet rule to fill up the electrons in the structure. Then you switch to VSEPR theory to be able to predict the shape. Okay, let's take a look at a couple more examples. Let's go ahead and see if we can draw the Lewis structure and predict the shape of the molecule NH3. Okay, so first write out the atoms, the number of atoms. So there's 1 nitrogen and 3 hydrogens, and each nitrogen has how many valence electrons? 5. You got to find that from the periodic table. And then each hydrogen has 1, but there's 3 hydrogens, so that makes it a total of 3. If you add these together, you get 8 valence electrons. Now, between the nitrogen and the hydrogen, go to the honk 1, 2, 3, 4 rule and take a look at which one forms more bonds. It's the nitrogen, so nitrogen goes in the center, and then go ahead and symmetrically arrange the hydrogens around the nitrogens with a single bond. Just as a reminder, these are how you draw the bonds: single, double, triple. Each bond represents 1 electron pair, and that's the number of electrons. Okay, so we drew 3 bonds for the 3 nitrogens, and that's where we stop for a second. Now let's look at the terminal atoms and take a look. Are they happy? Are they satisfied? And how do you know? You look at the octet rule and the duet rule. So since they're hydrogens, they each need 2 valence electrons. Indeed, they have 2. So we don't have to worry about the hydrogens anymore. Let's look at the nitrogen. Nitrogen wants 8, but it has 6, right? 2, 4, and 6. And so we actually used up those 6, so that leaves us with 2 electrons, which we're going to plonk on top of the nitrogen. Now these 2 electrons, they're also called lone electron. That's 1 lone electron pair. If there's more than 1 pair, you call them lone pairs. Okay, so that is your complete Lewis structure. Now, in order to predict the shape, we're going to use VSEPR. Okay, so to use VSEPR, we have to count the electron groups. So That is one group, that is 2, 3, and then the lone electron is a fourth group. When there are 4 groups, that makes a tetrahedral shape, okay? So I'll just try to draw that shape. If you just, as a reminder, a tetrahedral shape would kind of look like a tripod. There's going to be one dark arm that's coming out towards you, out of the board. One arm is going to be in the board. There's another arm that's going to go away from you, behind the board. And then there's another arm on top, which is going to be in the plane of the board. Okay, so that's the tetrahedral structure. So out here, the 4 electron groups, we can put the lone pair going above us. And now we have one hydrogen coming out this way. We have another hydrogen in the plane of the board, and then we have the final hydrogen going behind the board. Okay, so if you kind of look at this, this kind of makes something called a pyramidal structure, because I'll just use a different color out here to denote this. Notice carefully, this is one face of the pyramid. That is another face of the pyramid, and that is another face, and there are 3 faces of this pyramid. Okay, so therefore the shape of this molecule is going to be trigonal pyramidal. Pyramidal for obvious reasons, because it looks like a pyramid, and if you recall, we cover up the lone pair, so the lone pair does not factor in the shape. And it's trigonal because there are 3 faces of the pyramid. Okay, let's take a look at drawing the Lewis structure for a very simple molecule, CO, carbon monoxide. Let's go ahead and count the valence electrons. It's going to be, for carbon, it's going to be 4, and for carbon, it's going to be 4, and for oxygen, it's going to be 6. Add them, we have 10 to go around. Go ahead and connect the 2. In this case, since there's only 2 atoms, we don't have to worry about which one's going to be in the middle. We connect the 2 atoms, and then what we do is we connect them with a single bond. And then take a look, we actually used up 2 of those 10 electrons, which leaves us with 8. Now to distribute those 8, all we're going to do is put 2 on each of them in turn till we exhaust the 8. So that's 4, 6, 8, and 10. That's a total of 10 electrons. Done. Now, let's look at the octet rule. Both of these elements want to form an octet. Does oxygen have 8 electrons around itself? 2, 4, 6. It does not have 8 electrons. Does carbon have 8? 2, 4, 6. Does not have 8 electrons. So in order for them to have 8 electrons, what we're going to do is they're going to share some of the lone electrons to form multiple bonds. Okay, so and it doesn't matter who shares first, so let's go ahead and take off 2 from the carbon and put them in between the carbon and the oxygen as a double bond. So now when we do that, notice carefully, oxygen has 8, 2, 4, 6, and 8. But carbon still has 6, 2, 4, and 6. So now it's oxygen's turn. You cannot just take away from one element. You have to take it in turns. Okay, so once carbon gives, once oxygen gives. So we take away 1 from oxygen, and now we have 3 out here, 3 bonds in between the carbon and the oxygen. Now oxygen has 8, 2, 4, 6, 8, and carbon has 8, 2, 4, 6, 8. Everyone's happy. Octet rule is satisfied. Okay, but as a result of this, we ended up with a triple bond. Okay, which is fine. Okay, now once we have the triple bond, we have to kind of figure out what's the shape of this molecule. So how many electron groups in between are we dealing with? We're really only, if you just look at the middle of the molecule, we're just looking at 1 electron group, because these 3 bonds are all between the same atoms. They're treated collectively as 1 electron group. When there's 1 electron group, okay, 1 electron group, then your structure, your shape is linear, which literally means it's one straight line. So you can just view this like this, going in one straight line. Okay, All right, let's take a look at another example. This example is carbon dioxide. You have 4 valence electrons for carbon. For each oxygen, there's 2 oxygens, so that's 6 each, so that's 12, so that's a total of 16. We put carbon in the center because according to the Honk 1, 2, 3, 4 rule, carbon should make 4 bonds and oxygen should make 2. That means carbon needs to be in the center. Flank the carbon with 2 oxygens on both sides for symmetry. And then each of them has 2 electrons, so that's take away 4 from the 16. That gives you a total of 12 remaining. And then those remaining 12 will be put on the terminal atoms till each of them has a complete octet. So now see, each of the oxygens only has 2, so they need 6 each. And there's 12, right? So we can put 6 on that oxygen and 6 on this oxygen. Now the oxygens are happy, but the carbon's not. So how do we make the carbon happy? We share electrons. So if I pull 1 electron from there, make a double bond, that gives this carbon 6 electrons. I'm going to pull one pair from there and make another double bond. That gives the carbon 8. Notice carefully, the oxygens still have 8 each. Okay? Now that we have that, take a look at the central atom. We've got to predict the shape. If you look at the central atom out here, how many electron groups are on the central atom? 1 and 2. So if you have 2 electron groups, the way you can arrange 2 electron groups is essentially the way you arrange them to be furthest away from each other is a straight line going in opposite directions, right? So this would also be, so the structure of this would also be linear. Therefore, the shape of carbon dioxide, the carbon dioxide molecule is linear. Let's take a look at an example where we have H2CO. I didn't draw that oxygen properly. Let me redraw that. H2CO. Now we have quite a few atoms in this molecule, okay? So to draw the Lewis structure, we need to first count the valence electrons. So valence electrons. So we have 2 hydrogens, so that's going to give me a 2. Carbon is going to be 4 and oxygen is going to be 6. We add them together, that gives me a total of 12. Between these 3 types of atoms, carbon is going to form the most bonds, so that's going to be the central atom. Okay? And then we're going to arrange the remaining atoms symmetrically around the carbon with single bonds. There you have it. Okay? Now once you arrange them with single bonds, let's go ahead and count how many of the 12 we used up. 6. So that leaves us with 6. And the hydrogens are already happy because of the duet rule. Therefore, the only 2 we have to look at to give more electrons is the carbon and the oxygen. So let's go ahead and fill out the terminal oxygen first to have 8. And that completes those 6. So we have no more left. But now the carbon is not happy yet. So we erase 1 pair from there and put it in between the carbon and the oxygen. Now, carbon has 8, oxygen has 8, each of the hydrogens have 2. Once we have that, to predict the shape of this molecule, you got to look at the central atom and the electron groups around the central atom. So, the central atom is carbon. We have 1, 2, 3 electron groups. When you have 3 electron groups around the central atom, then those 3 electron groups will distribute themselves equally in space in one plane. Okay, so if you imagine a ceiling fan with 3 blades, how it's still in 3 dimensions, but the blades are equidistant in space. So that bond angle is going to be 120 degrees because 120 times 3 is 360. And since they're equal in space, you call them, and they're 3. So the shape of this is going to be trigonal planar. Okay. Let's take a look at how to write the Lewis structure for polyatomic ions. Okay. So polyatomic ions, and what we mean by that is if you have a group of atoms together and they have a charge on it, it's a polyatomic ion. Okay, so for example, let's say you have NH4 plus. That's a polyatomic ion. Now, two rules out here. If the ion, I'll write it out here. If the ion, so basically if it's a cation, that means it's positively charged, then you will subtract 1 from the number of valence electrons. If it is an anion, which means it's negatively charged, you will add 1 to number of valence electrons. So let's take a look at what's happening out here. Let's count the valence electrons. Nitrogen should be 5, and there are 4 hydrogens. So that's a total of 4. That gives me a total of 9. But since it's a cation, we're going to subtract 1. So I have 8 valence electrons to work with. Go ahead and put the nitrogen in the center, because according to the Honk rule, nitrogen should have 3 bonds and hydrogen should have only 1. And then surround the nitrogen with the 4 hydrogens symmetrically. Once you have the 4 hydrogens out there, let's go ahead and recount. 1, 2, 3, 4 times 2. So that's 8 valence electrons. Done. We have nothing left. Everyone's happy, by the way. Each hydrogen has a duet and the nitrogen has an octet. So once you excuse me, once you're done with that, you put a little bar like that, or you can put a square bracket, up to you, and put the positive charge outside of it. Okay. Once you put the positive charge outside of it, that's basically denoting that this is a polyatomic ion and that charge sits on this entire species. Once you have that, the next thing to figure out is what is the shape, right? So you have 4 electron groups, right? 1, 2, 3, 4. 4 electron groups. And if you recall, 4 electron groups is a tetrahedral shape. And because it's tetrahedral and there's none of them are lone electron pairs, so the shape is going to be, guess what? Tetrahedral. 4 electron groups, shape of this is tetrahedral. Let's talk about that charge for a second. If you had to ask the question, well, if you had to try to figure out exactly where that charge is sitting, on which atom, in order to do that, we have to kind of look at the concept of formal charges. Okay, so let me kind of introduce the concept of formal charges out here. Let me write that out here. Formal charges. Formal charge. So a formal charge is basically the charge is, you can think of it as a net charge, which tells you once all the electrons come together, what did the atom begin with? So how many valence electrons did it begin with, and how many does it end with? So it's kind of a way of bookkeeping, okay? Chemical bookkeeping, if you think about it. So how do you calculate the formal charge? So you can calculate the formal charge for each and every one of these atoms, okay? And the formula for that is number of valence electrons for that atom minus number of bonds minus number of lone electrons. Okay, lone electrons. That's the formula for the formal charge. And then if you add the formal charge for every one of these atoms, that should equal that net positive charge. Okay, so let's go ahead and calculate it. So in this particular case, since all the hydrogens are equivalent, we only calculated for one. And then for the nitrogen, well, I guess we could calculate for all of them, but it's the same calculation. And then we'll calculate for the nitrogen. So I'm going to go ahead and do it with red out here. Follow along closely. Hydrogen has 1 valence electron, so we're going to do 1 minus number of bonds. Well, it has 1 bond attached to it, minus number of lone electrons. There's no lone electrons, so that gives me a net of 0. Same thing for this hydrogen, it should be 0. For this one, 0, and this one, 0. Look at that nitrogen now. Nitrogen actually has 5 valence electrons How many bonds? 4 bonds, which gives me a net of positive 1. So this positive 1 charge, if you're going to take that positive 1, add it to the 4 zeros, that gives you a net of the positive charge. So that positive charge that's sitting on this polyatomic ion is predominantly residing on that nitrogen. Okay. Let's take a look at another example where we're looking at an anion. Okay. So there's a polyatomic anion. It's a CO3. It's a carbonate anion with 2 negative charges. Okay. Well, first let's draw the Lewis structure. So carbon has 4. Each oxygen has 6, but there are 3 oxygens, so that's a total of 18. And then because it's an anion, you add 1 electron, 1 to the number of valence electrons, but for each charge, okay? For each charge. For each charge, which means there's 2 charges, so I'm going to add 2. I'll just add it here. So each charge is 2. So that gives me a total of 24 valence electrons. Now I'm going to put the carbon in the center because oxygen can have 2 bonds and carbon can have 4. So I put the carbon in the center and then I surround it by the 3 oxygens, oxygen, oxygen, and oxygen. Let me rewrite this with a little more space down here. Carbon, oxygen, oxygen, oxygen. And then that took up 6 electrons, so that leaves me with 18. I'm going to put the remaining 18. I'm going to give 6 to each of the remaining oxygens. When I do that, now all the oxygens are happy because they have 8, but the carbon only has 6. So I'm going to just share one of these electrons, one of these lone electrons with the carbon. That still keeps this oxygen at 8, but now this carbon has 8 as well. And there you have it. I'm just going to write this a little differently for some space. I'm going to put a square bracket around that. That should have a -2 negative charge, or 2 minus. All right, so once I have that, now the question is, let's calculate the formal charge for each of these atoms. So this oxygen is going to be what? Number of valence electrons minus number of bonds. So valence electrons is going to be 6 for each oxygen. What did it begin with? 6 minus number of bonds, so that's 1, minus number of lone electrons, 2, 4, 6. That gives me a net of -1. I'll put that out here in red, -1. That oxygen should have the same calculation, so that should be a -1 as well. Let's go ahead and try that oxygen. That gives me, that should be 6 minus 2 bonds minus 4 lone electrons, so that's a 0. And then look at this carbon out here. That should give me what? 4 minus 4 bonds. So that's a 0 as well, but then red. All right, so if you add these all together, you can see that 0 plus 0 plus -1 plus -1 is going to give me a -2. And that's basically the formal charge for the carbonate anion. Now, let's talk about the structure of this. I forgot to talk about the shape or the structure of this. Well, there's 3 electron groups, right, around the central atom. 1, 2, and 3. 3 electron groups, which means it's going to be trigonal planar. Let's introduce the concept of resonance, okay? So in the last structure that we drew, we actually ended up with carbon. It was just as a reminder, it was for the CO3 2 minus ion. So we ended up with carbon with 3 oxygens around it. This one had 2 lone electrons, this one had 6, and this one had 6. And we had the charge out here. So for the sake of our discussion, I'm going to erase this charge so we're not confused. Okay. Now the question is, there are 3 distinct oxygens out there. They're not the same species. They're all called oxygens, but they're 3 distinct oxygen atoms. And the question is, how do you decide which oxygen atom to put the double bond on? So for the sake of our discussion, I'm going to call this atom 1, that one 2, maybe I'll write that outside a little bigger so we can see very clearly. I'm going to call that 1, 2, and that 3. Okay. So you could have done this. You could have drawn this structure where the double bond is on oxygen 3, and that would have had 4 lone electrons. This one would have 6, and this one would have 6 as well. So then, just to keep our convention the same, that's 3, that's 1, that's 2. Notice carefully, out here oxygen number 1 had the double bond, and out here oxygen number 3 has the double bond. So the question is, which one is correct? The answer is both are correct, because both of these are equivalent forms. So whenever you have a scenario where you can draw more than one equivalent forms, you connect them, you show them with a double headed arrow that way. These are called resonance forms. Why resonance? Because the electrons are jumping back and forth, so they're resonating. Okay, so you can think of these forms as being resonating between each other. So in reality, what does the molecule look like? Does it look like this, or does it look like this? In reality, it looks like a mix between the two. So it's going to look something like this: carbon, oxygen, oxygen, oxygen. Let's go and label that as 1, 2, and 3, and it's going to have a partial double bond out there, a partial one out here, and a partial one out here. Now what I just drew is called a resonance hybrid. So in reality, the structure is kind of a hybrid between these two, and actually there are 3, because you could draw a third structure where the double bond is between the carbon and the oxygen number 2. Okay, if that made sense.